All right, we're going to begin now. Welcome back, everybody. So today we're going to start week 6. We're going to be talking about two different types of distributions that I want you to be aware of. I think you know from previous classes, but just to kind of bring it back to your attention, okay? Before I begin, there's been some comments about the homework, so I just want to remind people of the metric. And I think by and large, people are scoring quite well, and the peer reviews are coming along well. Just remember, the peer reviews are worth 2 points. So if you don't do your peer review in a given week, that's 2 points you're missing. The homework is only 4 points, so think of the peer review as having 50% of the weight of the homework, okay? Ali? Okay. All right, so I encourage you to get your peer reviews done. And all right, so and a few more comments. If you are scoring people, let's say with a 3, 4, or a 5, or a 2, you should leave a little bit of a comment saying, justifying your grade, okay? So even if you say 4, please say everything looks correct. So we know that you think that everything looks correct, all right? And if you give a 3, don't just say, oh, there's some mistakes. Say what the mistakes are and what you think could have been done. So leave a little bit of feedback for the person, all right? One more thing. Once you've got your 2 peer reviews, I mentioned that we typically take the average of the 2 peer reviews as your grade for the assignment. However, if you are unhappy with your peer reviews, you just have to reply to your peer reviews and say what you think is wrong about the peer reviews, what you think the grade should have been, something like this. And we will take your feedback into consideration. So we call that a rebuttal. You are giving an argument against the peer reviews, all right? If you do not give a rebuttal, we assume you agree with the peer review grades, all right? So if you disagree with the peer review grades, tell us you disagree by replying to your peer reviews and leaving a little comment on what you think the peer reviewer was mistaken about, all right? If you just reply to the peer reviews and say, I disagree with these peer reviews, that's not good enough. We would like you to say a little bit about why you disagree with the peer reviews, okay? And so I hope that's clear. So if you disagree with the peer reviews, please reply. If you don't, we assume the peer reviews were fair, okay? Any questions? Are you okay with this? All right, great. All right, let's start today's topic. So today we're going to go back and have a look at the Bootstrap and take a look at a couple of different things that are going on in hypothesis testing, which we started talking about last week. So I want to just dig into hypothesis testing a little bit deeper with the aid of the Bootstrap. Okay, so we're revisiting stuff that you hopefully already know from a different light. All right, let's give this a shot. So to begin with, distributions. We talked about distributions the last few weeks, and you had this, what could be a simple question on your homework assignments about Google's malware detector. And we were basically told that they have this, there's a tool on Android which some malware meaning, mal just meaning bad, some bad actors on the Android Play Store. What is it called? The Play Store? App Store? Google Play Store? Play Store? Okay, Play Store. On the Google Play Store, who are turning off a feature so as not to get caught. Okay? So Google's trying to see the distribution of these apps that are turning this off. If there's an app whose frequency of turning this thing off is a little too high, significantly higher than others, then it's a potential malware. So they had a threshold value of minus 3.7, all right? And remember, this was from a binomial distribution that was large enough that we can approximate it as a normal distribution. And you were asked, roughly, how many apps do we think are getting flagged by Google every year, all right? Now, this is an approximation for a couple of reasons. One is, When we say minus 3.7, this threshold, what is this the threshold for? If there are apps that are currently on the App Store, we presume that they are above this threshold, right? That because otherwise Google would have flagged them and tried to remove them. There may be some number of apps that Google is still monitoring and they haven't yet flagged, so they might still be on the Play Store. Might still be on the Play Store. Okay? So one reason why I said this is an approximation, because I told you, assume there's about, when this article came out, there was about 2.5 million apps on the Play Store. So if we take that as the full inventory of apps, then what percentage is below this threshold? So the thing you have to be careful about is, and the reason I say it's an approximation, is that many of the apps below this threshold have already been removed from the Play Store. So that 2.5 million is likely just the good apps, okay? So I'm curious to see if anybody tried to assume that 2.5 million is this range of not flagged apps, and the minus 3.7 should be flagged apps. So that's another way of interpreting this, all right? But I think by and large, I'm okay if you just assumed that 2.5 million is the total number of apps, good and flagged, and that the minus and everything below the minus 3.7 threshold is going to be malware. All right, okay. And if you did that, then you just have to kind of find out what percentage of this distribution falls under this threshold. So that's using the pnorm function, and that's a very small percentage. It's 1/100 of 1% or something like this. Okay. And roughly 270 something apps will then fall under this. All right. Okay. Did anybody have any? Oh yeah, please. Question.
Should we route it into like?
Oh, good, great question. Should you round it off? You both works. If you round it off, it's because you're saying this is the number of apps. You don't expect 0.49 apps somewhere, right? At the same time, by not rounding it off, you are saying this is an approximation, and it could go either ways. So I could accept both. Actually, I could accept both. Okay. Out of curiosity, did anyone assume that the 2.5 million apps are above the minus 3.7 threshold since they're on the Play Store? Did anybody assume this? Yes? No? Nobody? So you all assume that the 2.5 million can include potential malware as well, right? Okay. A couple of years ago, I had a student ask me with a completely different perspective, which I really also appreciate. A student asked me, isn't there a different way of thinking about this problem? Which is that perhaps minus 3.7 is the low end for good apps, but it's the average for bad apps. So maybe what we can interpret is that there's two distributions of apps. There's good apps and bad apps, and perhaps good apps are over here, and there's a minus 3.7 threshold certainly, but maybe all the bad apps are around this minus 3.7 threshold. So when you tell us 2.5 million apps, are those the good apps or bad apps? Okay, I won't go too much into this interpretation, except to say I prefer the earlier interpretation, simply because this interpretation suggests that we are only discarding half of the bad apps, since the distribution for bad apps is centered around minus 3.7, if that was your assumption. So I would like to think Google is trying to flag most of the bad apps, not just half of them. Okay, so I would kind of go with this interpretation for now. All right, but I'm curious to see if there's other interpretations on the assignment. So, but hopefully that got you a chance to play with distributions and the pnorm function as well, right? Great. Okay, moving on. The other problem you had was about Verizon's customer response times, all right? And as I mentioned, the data is real, but the question is mine. The question is fictional, okay? And I say this because I don't want Verizon to sue me, that's why, okay? All right, so it should be fairly straightforward, but let's take a look. So we load the data, and we get the time out of this data set, okay? do notice that this data is in CSV formats. So let's go take a look here. So let's view the file. If you look at the file, there's 2 columns of data, and they're separated by a comma. So the headers tells you that there's a column called time and a column called group. And then here there's like a time and a group, a time and a group. So each row is actually got 2 values, all right? And they're separated by a comma. So this file format is typically called CSV. It is the extension of the file, but it stands for comma separated values, all right? And there's several ways of loading this. One is to use the read table command that we may have seen earlier in class, and tell it that there's a separator, which is a comma, in there somewhere. Another approach might be simply to say that I'm expecting a CSV file. So R comes with a read.csv command, which assumes 2 things. One, it assumes that there is a separator, which is a comma, as you can see right there, okay? And it also assumes that there's going to be headers to this file. So we see the headers is equal to true, all right? So you can use read.table, which is a more general form, or read.csv, which is just to read this type of CSV file, all right? And for those of you who've done analytics before, you probably know that CSV is one of the most common formats in which we exchange data for analytics purposes. Not for other purposes, but at least for analytics, all right? So we should be able to read Verizon.csv quite easily like that, and then we can extract the time, right? So now time should have some kind of format like this. So I asked you to visualize the density, and it's not the density, I asked you to visualize the time. So there's 2 ways of visualizing it. One is to use a density plot, or a kernel density plots, okay? So it looks like this. And I'm putting the mean time as a dashed line here. And you can see that the mean time is, first of all, it's not in the center of the big hump of the distribution, all right? In fact, the mean time, there's very few values that correspond to the mean time. So it's a good demonstration that the mean or the average doesn't actually have to at all mean that is a typical value. Here the mean is a very atypical value, all right? It's a very unusual value, in fact, even though it's the mean, all right? Great. Another way of visualizing it could, of course, be a box plot. And the box plot does not show the mean, so I'm going to show the mean myself. It does show the median as this dark line in the middle of the box itself, okay? And there are whiskers on 2 ends of the box plots, and everything outside these whiskers, what are these points? Outliers, right? So these are all outliers. And you can see there's a lot of outliers using, which rule is this using to detect outliers? There's a name for this rule. What kind of a name for the rule? Anybody remember? What's that? I don't think so. I don't think so. It starts with the number 1. Yes, IQ. It's the 1.5 IQR rule, okay? So you compute the interquartile range, the IQR of this data, and then everything 1.5 IQR to the left of the first quartile or to the right of the third quartile. So this is about 1.5 IQR to the right of the third quartile. All these points are considered outliers, all right? So it's the 1.5 IQR rule. You can go back to week, I forget, 3 or 4, where I think it was week 3 when we discussed, week 1? Week 1 we discussed the IQR rule? Okay, fantastic. All right, thank you. All right. Out of curiosity, how many of you decided to go with a density plot? How many of you visualize this with a density plot? Oh, okay, we have converted the whole class into density fans. All right, how many of you chose a box plot? One person? You all forgot the box plot? Ooh. You did? Okay. How many of you did both? Box plot and density plot? Okay, one. Okay, great. Me too. So they both have their advantages, right? So the density plot, it is more pleasing to look at. I don't disagree with that, okay? And you can see the little bumps wherever there is values somewhere out there. However, the box plot gives you a quantile view of things and really shows you that the middle 75% of your data is definitely the middle 50% of your data is in fact before the mean. That's kind of crazy, right? It's the middle 50% of your data comes before the mean. So I think there's a value in seeing both. And certainly there's a value in seeing what the 1.5 Iqr rule would consider to be outliers. So I think there's a benefit to seeing both, all right? But I'll accept either. All right, cool. Then what did we do? So this was about visualizing the data. And then the next thing we looked at was, can we do a little hypothesis test here based on the manager's claim that the based on the company's claim that the mean response time should be like 7.6. 7.6 what? I don't exactly know. Seconds, that's a little too much, but this is just an exercise, all right? So bear with me, okay? So if this is the hypothesis, well, this is the value of the hypothesis. How would you actually write this hypothesis? I'm going to be a little bit lenient on how you wrote the hypothesis because I'm not really focusing that much of this semester's class on writing hypotheses and stuff like that. I hope you've had a class where you've seen that before, or maybe you'll have an advisor who'll who'll whip you into shape about this kind of thing, okay? But by and large, one way that I recommend you write hypothesis is with two separate hypotheses, and I think you've seen this before, which is to write a null and an alternative hypothesis. I'm very curious, how many of you wrote a null and an alternative hypothesis? Anybody? Okay, all right, almost a quarter of the people here. So generally speaking, when we're doing hypothesis testing, we are trying to compare two claims, all right? The claim that is made of the data and essentially the one that we're trying to disprove, all right? So this is the claim we're trying to disprove with the data, and if our data is different enough from the null hypothesis, then we say we have an alternative hypothesis that we would rather go with, all right? So if you've forgotten your null and your alternative hypotheses, go look back in your stats book about how these things work, all right? For those of you who did a null and an alternative hypothesis, how many of you went with a two-tailed hypothesis or a two-tailed test? Two-tailed? Okay. How many of you went with a one-tailed test? Oh, interesting. Okay, so the class is divided. I will accept either, all right? I'm very generous. So null and the alternative. So what would the two-tailed look like? The two-tailed test look like? So the null hypothesis would be that the population mean is 7.6. This is literally the claim in the assignment, actually. In the assignment doesn't say less than, greater than. The assignment just says, the company says it should be, the mean should be 7.6, okay? So it's reasonable, I think, to do a two-tailed test if you take the assignment description literally. If our data does not look like the mean is 7.6, then the alternative that we will go for is that the mean is significantly greater or less than 7.6, all right? However, I do greatly sympathize and respect the people who went with the one-tailed test, because I know the company's claim is 7.6, but the person who is suffering in this situation is actually arguing. Oh, this is a cut and paste error. Excuse me about that. Obviously, all right. So let me hide that. The null is that the population mean is 7.6 or less, because here in the assignment description, the person who's suffering from these low response times is saying that it's way too big. It's way too big. So it's fair to say that the null hypothesis is less than 7.6 or 7.6 or smaller, and the alternative is that it's bigger than 7.6. Okay. Could one of the TAs kindly slack me about the typo? Thank you. All right. Anyway, both work fine. But I'm going to do a two-tailed example. Yes?
I think I have some misunderstanding of the 7.6 minutes is too big. I think it's too small. Because I think the question want to prove that it provides a good quality of their service, so they spend a lot of time on.
I see. Excellent. Okay, so thank you for saying that. So there's two possibilities with the one-tailed test. How many of you said that the null, for those of you who did the one-tailed, how many of you said that the null is that the mean is 7.6 or smaller? And how many of you said that it's 7.6 or bigger? Oh, I like your way of thinking. You're taking the side of the claim, right? That the well, no, you're actually taking this. Excuse me. You're actually taking the side of the person trying to disprove the claim. You're taking the side of the person who wrote the article that I shared with you, right? That so you're trying to show that the null so let me get this straight. So you wrote that the null hypothesis is that the population mean is 7.6 or greater. Is that right? Okay. So there's two ways to write it, as greater and as lesser, and the alternative would be the opposite, right? However, I think when you for the purpose of testing, for the purpose of testing, I think you want to look at what the mean time actually is, right? And it's considerably bigger here, right? Than 7.6. And you cannot really set the null to be 7.6 or bigger because it's already bigger than that. So the alternative is usually taking the side of the data, and the null is taking the side of a previous claim, all right? And you want them to be the opposite of each other, right? But since the data is already telling us that the mean time is 8 point something, then that's got to be the alternative, all right? And the null has to be the other way around, okay? So I hope that helps. I hope that's a little refresher or reminder of how these one-tailed tests work, okay? I'll try to be generous about the scoring of the way you write the hypothesis, all right? Okay, so let's see, what did I do now? All right, so I've gone ahead, and this is the classical approach. I've found the mean, I've got the standard deviation, and I compute the standard error, okay? And again, the standard error is nothing more than the standard deviation of the mean, all right? So the standard error is a kind of standard deviation, but it's of the sampling mean, okay? I can now try to compute the confidence interval of the mean. And I do this by, there's a little, I think this is wrong. Hold on, let me jump here. Okay, I'm doing two-tailed, and I'm doing 99%. So I want 0.5% on one side and 0.5% on the other side. In the assignment, did I write 95% or 99%? I wrote 99? Oh, okay. I must have read the assignment when I did this. Okay. All right. So I'm actually looking at the 0.5% on the left side and the 0.5% on the right-hand side. So I'm kind of computing this quantile here. And you'll notice that the way I'm computing the quantile, I'm using this QT function. All right. So I'll look at QT. Okay. All right. So, and you will notice that the quantile for the T distribution looks like this. You give a vector of probabilities, and then you give the degrees of freedom. All right? So provide degrees of freedom as sample size -1. Okay? This is, by the way, where you would tell it, are you looking at are you looking at single tail or upper tail or something like this. All right? All right. And then I compute the standard, the confidence interval by just multiplying this quantile by the standard error. So it's the 99% for this t distribution will be -2.58 and positive 2.58 times the standard error. And this gives me the confidence interval of the mean. All right. And if I want to go with the t-value, which is kind of like a standardized difference, if you will, then the difference we're talking about is the mean time minus the hypothesized time, and we're just kind of standardizing it with the standard error here, and we get this t-value. All right, and we can ask, what is the cutoff t-value? So if our null distribution looks like this, so if we are expecting t-values to be centered around 0, where is the threshold, or what is the p-value here? And we use this pt function. All right. Yes. Question.
Sorry for the confidence interval. Is the method with the formula 2.58 correct?
Yeah, it's correct. We've used 2.58. That's correct. However, I do encourage you moving forward to not just use 2.58, but actually ask what is the threshold values that I'm really interested in, because it could depend a little bit on your sample size. Now, as your sample size gets bigger, it'll get closer to 2.58, right? But why not get an extremely precise value, right? Let me say one more thing about this, because this is a really good question. Should we just use 2.58? Hey, why not just 2.5, right? It also depends, what is the precision of your answer, right? You'll notice here, I'm trying to give the answer to 6 decimal places. That's probably overkill, but I'm giving it to this many decimal places. If I'm giving it to this many decimal places, then I probably want my quantile values to also have the same precision, all right? It doesn't make sense to say 2.58 here and then a big precision here, because it doesn't match. All right. So since I want to give it a little bit more precision, I'm using something other than, I'm using more precise values of this quantiles. Does that make sense? Okay. So it depends on the precision that you're trying to give the answer to. All right. Now, realistically, even if you said 2.5 or 2.6, it's probably okay. Why? Because the population mean you're given is only to 1 decimal place. Right? So it's any other precision you add to it isn't really adding much value to it. All right. So I would even be okay if you just said -2.5 or 2.6 or positive 2.6 for that matter, because the numbers you're given are only to 1 decimal place. All right. Okay, but I did go with more decimal places because I wanted to make a point here, which is 7.6 actually falls within this confidence interval if you do it to this many decimal places. All right? All right, and then here's my p-value, and I'm simply asking what percentage of the null distribution lies to the right of this t-value that I calculated. So remember, pt gives you the percentage to the left, so 1 minus pt gives you the percentage to the right. Okay? And again, for added precision, I'm not using p norm, I'm using pt, and I'm giving it a degrees of freedom. All right? And so this tells me that 0.005, so half of a percentage of the expected t-values lie to the right of this value, okay? More than half. So technically speaking, the company is in luck because we are right at the threshold of being able to reject it, but just before the threshold of being able to reject it. Now, I don't know what precision each of you answered it to. How many of you used a precision that allowed you to reject this hypothesis? Was anybody able to reject the hypothesis? Yeah? Okay, so it depends what precision you're using, perhaps, all right? So this is a very borderline case, all right? And you can see in my figure here that the t value I get is just a tiny whisker to the left of the threshold if you use the precision I used, all right? Now, would I realistically look at these results and say, Verizon is correct? Would I? I don't know. I don't think I would be that hardcore about confidence intervals, all right? Somebody might be tempted to say, you said 99%, and yes, we got it right within 99%. You have to absolve us. At the same time, I would say you are so close to the threshold that perhaps I need to collect some more data to see what this looks like, all right? Maybe more data would disprove this, perhaps. All right, yeah, question, Meta.
Is there any interrelationship between t value and p value, right?
Yes.
Is there any bar that if the p value is 2.58, the p value should be this?
Actually, they should agree perfectly. They should agree perfectly because the p-value is actually computed from the t distribution from this t-value. All right? So you should not find any discrepancy between what the t-value tells you and what the p-value tells you. You should not. Okay? All right.
So is there any bar that if there is 2.56 suppose, then the p-value should be 0.01 or something?
No, it works the other way around, where you actually start by saying what is your confidence interval. All right? And that confidence interval kind of tells you that we are looking for p-values, in this case, smaller than 0.005. Because we chose a confidence interval of 99%, so an alpha of 1%, if you will. So we're looking for for half a percentage on either side. Okay? So it should all line up perfectly. All right. Okay. Now I have a question.
For example, for all of us that we did just one tail.
Yes.
In this case, of course, this changes because for me, like I did one tail and I rejected. This
Yes.
case, it was like literally like a little bit only like
Over.
outside. Yeah.
Okay.
So that's why I rejected. But also because if you see, and I may be wrong, and please correct me if I'm wrong. Like if the p-value, as far as I know, if it's too small or like really really small, you can reject the null hypothesis.
Yeah, if it's smaller than the alpha, like if it's smaller than 1 minus the confidence interval you've chosen, yes.
Yeah.
So if you use a one tail, you probably could reject this, yes.
Yeah, because for example, for p-value, I got the same.
Yes.
Same as, of course.
Yes.
But like, for example, the rejection point, which is with alpha of 1%,
Yeah.
I got 2.32. So
Okay.
of course, like I rejected because it was like
Yes.
smaller than the
So you got the same
value.
t-value as me.
I have the same t-value,
Right.
but I have
Your threshold was much
the
smaller, right?
alpha of 1%, so
Yeah.
it will be 2.32.
Yes. That's totally fine. So you can reject it at 1%, all right? And actually, in many ways, that's probably the more rigorous way of looking at this problem, because actually what Verizon is claiming is that they are 7.6 or less, right? They're not saying we are at least 7.6 or we are on average. It is so if you read it that way, I totally sympathize with that, all right? So that's totally fine, okay? So if you use the one tail, you probably rejected this, all right? Okay, and even if you chose two-tailed, maybe you didn't reject this, like in this case. However, I wouldn't stop there. I wouldn't say, oh, you're just like 0.0002 over, like I don't reject it. To me, it doesn't work that way. To some people, it might. Here, I would really say we need to collect more data because we're so on the, on the line here that we need more information. Okay. Okay. All right. So that's the classical way of looking at this problem, and then there's the Bootstrap way of looking at this problem. All right. By the way, before I move to the Bootstrap way, do note what we are really doing here is we know that there's a null distribution and that there is an alternative distribution of t, right? And if you reject, you're saying, I believe the alternative distribution is the better distribution to describe the t values that researchers are getting, not the null distribution, all right? And if you do not reject, you're kind of in favor of the null distribution. either way, there's one point I want to make here, which is when you do this kind of classical hypothesis testing, you are really comparing things to the null distribution, right? You're saying if the t-values are 0, then what is the threshold, in my case, on two sides, beyond which I would reject it? So you're basing yourself on the null distribution, right? So that's what you're doing with classical hypothesis testing, all right? Okay. Let's look at bootstrapping for a moment, all right? So this was my bootstrap function, and I know that this homework assignment is going to ask for three things: the mean, the difference, and the t-value of to bootstrap the t-value as well, right? So my bootstrap function actually does all three, and it returns all three. So you'll notice here, basically my boot function is, it's resampling, it's computing the standard error, it's calculating the sample of the mean of the resample, the difference of the mean of the resample from the hypothesized mean, and the t statistic as well. And then I'm just returning a vector with all three values: the mean, the diff, and the boot. Okay, excuse me, and the t value. And then I call replicate on this boot function. All right. What happens? Like in previous classes, perhaps I have been only returning one value from my boot function. But this time I'm returning three values in a vector. What happens when I replicate this? All right. So just to give you a little demonstration, where's my demonstration? Where is it? Where are you? It's right here. Okay. So just to give you a little demonstration here, if you replicate and the return value is a vector, then what replicate does is it treats the return vector as a column vector. So it returns it as a column, all right? And since I replicated 5 times, I will have 5 columns. 3 rows, because that's how many values my vector is returning. This is just a demonstration of what happens when you replicate a vector, all right? R treats the vectors as a column. We'll come back to this in a few weeks' time. So therefore, once I have replicated, my boot stats variable is going to be a matrix with 3 rows and 2,000 columns. All right, 3 rows and 2,000 columns. That's what I'm going to get back from my boot function. All right, cool. And if I want the means, so the means, the differences, and the t statistics are just different rows in that matrix that comes back. It's row number 1, 2, or 3. All right? Great. So here's the bootstrap means. I just kind of like, I gather them from this boot function of mine, and then I plot the density of the means. That looks great. Then I plot the density of the differences. On top is the distribution of the means, and below is the distribution of the differences bootstrapped. What do you notice? Anything? It's the scale changes, but the shape is actually the same. It's the same shape, okay? More or less. There might be slight differences, but it's a very similar shape. And it's just that by and large, the scale has changed, because the scale is now showing you differences down here, whereas that's showing you mean values up there. Okay? All right. And what else have I done? I've put the hypothesized mean as a dark line, and I've drawn the 99% confidence interval of the means and the differences with a dashed line. So you notice in bootstrapping this, actually, even though I'm getting these the hypothesized value is outside of the confidence interval, okay, when I'm bootstrapping it, which is different from my classical approach. All right, and then last of all, I can look at the Bootstrap T Statistics as well. Do you notice something now? When you compare my Bootstrap T Statistics to my Bootstrap differences, all the mean, you notice anything? The shape is actually changed. the shape is actually changed. Why has the shape changed here? It's because the Bootstrap T statistic has a little bit more information than the mean or the difference. And that extra information is the standard error of each bootstrapped resample. Each time I bootstrap this sample, I get not only a mean and a difference, I'm also getting a standard error now of that resample. And I'm using that, okay? So when I use the standard error information as well, the shape actually changes a little bit. Right, so just I want you to be clear that the means and the differences are going to be very similar because essentially they're both using the same information, the mean of the resamples. But the Bootstrap T values has one bit more information. It's got the standard error of the resamples also built into it. Okay? And the shape changes. The shape changes, and actually the hypothesized, well, the actual T value is outside, the T value that I would expect, which would be 0 if the hypothesis was true, is outside the 99% confidence interval. Okay? All right. Similarly, the difference one would expect would be 0 if the hypothesis was true. All right? A couple of points I want to make here. One was about the shape of things, right? And why the shape is different. We have a bit more information here. Just because, and because we have more information in bootstrapping the T values, we actually prefer to bootstrap the T values rather than just the means or just the differences, all right? This extra information can come in helpful. So by and large, the most accurate way of bootstrapping is to bootstrap the statistic that you are interested in. I know this is a big disappointment because perhaps one of the promises of the bootstrap seems to be, I don't have to know statistics anymore. I can just bootstrap everything. You can bootstrap everything, but if you want a more accurate result, you should actually bootstrap the statistic you're interested in. In this case, it's the T statistic. All right? So, all right. So that's one thing. That's something I want to point out about the Bootstrap T values. One more thing I would like to point out. What distribution is this that I'm exactly? Yeah. Oh, sorry, Stephanie. Question first.
Sorry, yes, you can input anything, like for example T-square or like.
Yes.
Anything.
You can bootstrap anything. I can see all the possibilities in your head, like the world is changing. Yes, you can bootstrap all the things. All right. Perhaps later this semester I'll describe some situations where you don't want to bootstrap. By and large, I'll say this. If you're interested in distributions, bootstrapping is beautiful. All right? If you're interested in data, bootstrap is not beautiful because the bootstrap, as we saw last week, is a highly destructive process. It wipes out 30% of your data, like a third of your data, and replaces it with clones of the rest of the data. So it's not great for looking at individual data. It's great for looking at the distributions. All right. Okay. All right. And so then there's one more thing which I want to ask, one more question I want to ask. What is this distribution that I just created here with the bootstrap? So this is a T distribution, correct? Because I'm literally bootstrapping the T statistic. Yeah, question.
Professor, in this case we have three kind of T testing, right? The traditional one don't reject the Null Hypothesis, but the three other one will reject the Null Hypothesis.
Right.
So in this case, what kind of
What should we do? Okay, so your question is, what should we do? Should we believe the regular classical approach, or should we believe the bootstrapped approach? Can you give me one more week to answer that question? Or at least till the end of today to answer that question? Give me a little bit longer to answer that question. I'll try to start hinting at which directions we should be preferring slowly, okay? All right. But I want you to appreciate, as you already have, that there is a discrepancy. One approach is saying, don't reject. The other approach is saying reject. All right? And both two-tailed. All right? So I want that to bother you for a little bit longer. All right? You'll remember the answer better then. Okay. So of these three distributions that are bootstrapped, only one is a T distribution. Right? Because this is literally the T statistic. Notice that these two should actually approximate a normal distribution, not a t distribution, because the sampling means are, if you have big enough samples, they should be approaching normal distributions. The last one is actually a t distribution, which could come very close to a normal distribution, but it is better thought of as a t distribution because it is the t statistic, and it has the family of t distributions has a couple of other properties that I'm going to go into in the coming slides. Okay, so this is the only one that we can really say this is a t distribution. Now, I showed you two t distributions before, the null distribution of t and the alternative distribution of t. I said in classical testing we're kind of focused on the null distribution and we're asking where's the threshold, right? Which distribution is this one? Is this the null distribution or the alternative distribution? Think about it for 5 seconds. You're not even thinking about it. What are you guys doing? Okay, done? Which distribution is it? Is it the null distribution or the t distribution? I'll show you this picture again as well. All right, we're going to take a vote. This is a democratic class sometimes. When I choose to be, it's democratic. When it's not, it's not. How many of you think we are bootstrapping the null distribution? All right, some hands. Any hands? What is that, Mehtab? Is that a hand or not? You cannot. Okay, all right. How many of you think we're bootstrapping the alternative distribution? Several more hands. Okay. Those of you who think we are simulating, if you will, the alternative distribution, why do you think that? Somebody? Anybody? I should have a little resampling code on my computer so I can just pick out one student at random. Like, you are today's Bootstrap sample. Anybody? What is the Q you're looking at that makes you think it's the alternative distribution? Anybody? Oh, come on. I'm not grading you on this. I'm just asking you. Can't be this terrified of it. Why do you think it's the alternative distribution? Stephanie.
I may be super wrong. Because for me, depends on the formula, right? If you're taking the formula, you're taking x minus u divided by standard deviation.
Okay.
So you're taking the hypothesis that the company is giving you.
But wait. If it's the hypothesis the company is giving you, that's the null distribution.
Yeah. But then you are subtracting with
the hypothesized mean.
Exactly.
And
so that's
the
why I think that you
okay.
are alternative.
So you're saying the t value, when you're simulating the t value, it's as if you're simulating the alternative argument.
Yes, exactly.
Okay, I could buy that. Any other reasons why people think this might be the alternative distribution? Visually speaking, that's mathematically speaking. Yes. The number on the x-axis. So here, the null distribution is centered around 0. The alternative distribution is centered around the t value that you got, right? What is this centered around? It's centered around the t value. It's not centered around 0. Okay? In fact, the null distribution would be centered around this black bar here. It would be centered around 0. It would be a similar shape, but over here, centered around this. I cannot draw it with my mouse cursor, but like this, okay? Just pretend. All right. So this actually is the alternative distribution that we have simulated, which is interesting because this is not what classical hypothesis testing is looking at. It's looking at the null and the thresholds of the null. Here we're looking at the alternative, and I'm drawing these 99% confidence thresholds around the alternative. Wow. Okay, I'm doing this completely the other way around. I'm looking at the alternative distribution. Interesting, yeah? Okay, why am I looking at the alternative distribution? Does it make a difference or not? Well, why don't we look at both? Since we have clearly simulated the alternative distribution, let's try to simulate the null distribution as well and see if there's a difference between these two distributions. Are you with me? Yeah? Okay. All right. So let's just try this out. So and I'm going to go here. All right. So let's try this. I'm going to load the Verizon data. This is the hypothesized mean. Okay, here is my new boot function for only the t values. Okay, and let's take a look at this boot function. I've got it on your slide over here. All right. So I'm only interested in the t values this time. So I'm resampling. I'm computing the standard error of each resample, and then I'm computing the alternative value of t. That's what we did on the homework assignment. Okay. Now, how do I simulate the null distribution of t? Well, we know the null distribution of t should be centered around 0, but it should not be 0 every single time. But it should be centered around 0. On average, it should be centered around 0. All right? But it should not be 0 every single time. It should be distributed around 0. What could I subtract the mean of the resample from such that the distribution will be centered around 0? Well, what is the... So it would be... Actually, the answer would be, I would subtract from the mean of each resample the value around which these resamples are revolving, which is the original sample itself. Okay? So I'm taking the mean of the original sample, not the hypothesized mean. All right? Why am I doing this? Because I'm expecting that each resample is based on this original sample, right? I just sampled from the original sample. And the means I'm getting from the resample should be, on average, equal to the mean of the original sample, right? So I'm using this little trick where I am subtracting the right information so that I will end up with a distribution that is, which on average, whose average value is going to be 0, just like the null distribution is. All right. So do you see this little magic trick of mine? Well, I didn't invent it, but it's a magic trick regardless. So because I want to get, this is my current distribution of the t values, and I'm trying to simulate now the null distribution. All right. The null distribution is basically saying the null distribution should look like the hypothesis is correct. So what I'm simulating here now is a world in which the hypothesized mean, rather than being the value that the company claims, is a value that is going to be correct. I'm choosing the hypothesized mean that is going to be correct, which is going to be the mean of my original sample. All right. So I'm basically simulating a world in which the mean of my data was the hypothesis. All right. And this gives me a null value of t, which should be on average 0, because on average my resample mean should be almost exactly my original sample mean. It'll be, of course, a little bit this way and that way. That's exactly what we want. All right. And here, once again, I'm going to return a vector of values, the alternative value and the null value, replicated 2,000 times. My first row is going to be the alternative values of t. My second row is going to be the null values of t. All right. And let's take a look at this. Well, you've already seen it, but let me just run it to show you I'm not kidding. All right. So bootstats t is going to be, I can't really see it easily. Can I see at least one row of it? That's one row. Can I see 2 rows of it? No, R refuses to show it to me in a nice way. All right, you just have to believe me. All right. So my alternative, did I just bootstrap this or not? Okay, that was quick. My alternative values of t are the first row, and I can plot it out with the average value of those T statistics, okay? And my null values of T will be the second row, and I'm going to plot it out with a dashed curve, all right? And then, all right, the 99% confidence interval of the null distribution now is what we're seeing. Okay, and so this is what you're seeing here. And here too, you're seeing now that my average T values, or the T value that I got from my data, is actually outside this 99 confidence interval of the null distribution as well. All right. So if this is the case, which one should we be bootstrapping and taking a look at? Couple of things to consider. First of all, do you have anything you would like to say about these two distributions that you're seeing here? Do you notice anything? The shape is different. These two distributions actually don't look exactly the same. I mean, they have some similar features, but they're different, right? I mean, you could just say, oh, one is shorter and wider than the other. That's true. The null distribution in this case appears to be shorter and wider. However, you also notice that there's some features, like there's a little bump on the right-hand side of this thing that is not there on the other side, on the other distribution that prominently. These two distributions are slightly different. Okay. Does that make sense? Should they be different? Should they be the same? So one thing to realize about T distributions is their shape really depends on their centrality, on where is the center of the distribution. Okay? And by and large, this is from Wikipedia, as T distributions walk away from 0 as the center, their shape becomes skewed. They start getting skewed. All right? And here I'm plotting a perfect T distribution. Okay, this is a perfect T distribution. If you're interested in how I'm plotting a perfect T distribution, my code is up here. I'm literally creating a sequence of X values and then calculating densities, null and alternative densities. All right? And this is the perfect view of T distribution. If you had a perfect T distribution, this is what it would look like. Centered around 0, it's got a near normal form. But when they shift away from 0, you notice they begin to skew to the right or to the left, depending on which direction they're moving in, right? And by skewing, I mean the right-hand tail of this distribution is actually fatter than the left-hand tail of this distribution. All right? So you have to be careful when you're looking at T distribution. And I think there were some questions about this online, about like about how should we find the confidence interval of the T distribution. You need to be careful in realizing that the alternative distribution is not symmetrically distributed. So if you're just doing, if you're doing the alternative distribution of T and saying, screw the quantiles, I'm just going to do plus or minus 2.58 or 1.96, you're going to be a little bit off because the alternative distribution is not symmetrically distributed. Okay? I'm not going to go into the stats behind it except to say that T distributions, you usually know them as having like a degrees of freedom. They have one more parameter we don't typically talk about. It's the non-centrality parameter. And there's one more parameter in the T distribution that tells it how much towards 0 is it or how far from 0 is it. Okay? And in my simulation, I've just used the T value as a non-centrality parameter for T to simulate this alternative distribution of T, a perfect alternative distribution of T. All right? So, why am I saying this? First, if you are simply looking at the alternative distribution, please don't use plus or minus some threshold value. Look at the quantiles. Okay? Look at the quantiles. Second of all, So that's the danger. So what about the null distribution? I said the null distribution should look pretty close to perfect, right? It should look like a normal distribution. So should we just be simulating the null distribution instead, and then we can use our plus or minus logic? Will the null distribution always look normal? According to classical statistics, it should look normal for high degrees of freedom, right? But let's take a look at another example than your homework example to see a situation where that may not be the case. Okay? It may already not be the case in your homework example. I'm not entirely sure. But let's look at a case where visually it should look a little bit different at least. All right? Cool. So I'm going to move to a new example. And before I do that, let's just take a breather. Relax a little bit, stretch out. Don't be so nervous. It's just computational stats, okay? The tension is too high, I can tell. All right. Okay, good. Let's just stretch out a little bit. All right, good. All right. Okay, let's look at a different example. All right. So this is a different example. Once again, this data is true, and the scenario is also true. Okay. But it's a very small data set this time, okay? It's not a nice big data set, it's a very small data set. Okay, so let me read this out to you. I feel like this is middle school, but let me read this. Or in middle school, I would pick one of you to read this out, right? That's how we would do it. Okay, but you're paying customers, so I can't embarrass you, so let me read it out myself, okay? So here's the story, and I'm putting it in quotes because it's not me, it's somebody else who's writing this, okay? In fact, the person who's writing this is the owner of this website called sigmazone.com. What is sigmazone.com? I'm glad you asked. What is sigmazone.com? Last I looked, and this was some time ago, sigmazone.com, it is an analytics website, but it's one that's really promoting coaching and tools to using Excel to do analytics, Microsoft Excel. Okay, so anyway, somebody has this website, sigmazone.com. It looks like a consulting company that also makes some analytics tools for Excel. So here's the message, and I think I haven't changed it very much. I think I've almost hardly changed it, okay? So the owner is saying, I received an email from an irritated customer which says that my website is very slow. The most obvious solution to a slow website would be to notify my web hosting company, Alentis. So this person has his website, sigmazone.com, and they're not running it on their own. Well, they probably are running it on their own server, but they're not running it on their own server. They are renting a server from a web hosting company called Alentis. Okay, again, the name of the company is true, but don't sue me. Okay, all right. I did some preliminary testing, and it did appear that my site was not only slower than some famous websites like Google and Corel. What the hell? Corel's like ancient. Anyway, but my website was even slower than Alentis' homepage. And I was more than a little irked. Irked means, what does irk mean? Irked? What's that? Pissed? Is that what you said? What's the word you would tell your mother if she asked you, what does irked mean? Would you be like, Mom, it means pissed? No. You might say, yeah, pissed, or upset, or just a little frustrated. It's something between frustrated and upset. It's like a nice combination of those two things, okay? So a little irked that the company that I'm paying for hosting, Alentis, has a faster website than I do. Of course, I can understand why this person is upset, right? So if I chose to do nothing and my site was truly slow, my customers would suffer. If I chose to do something, but in reality my site was not slow, I would be basically wasting a lot of time. So I cannot act on a single data point. to act on a single data point would be folly. God, English has so many weird words. What is folly? Silly, it would be silly. All right. The differences in speed could be due to my local internet connection, the day or time in which I ran the test. Maybe Alentis was doing a server update at that time. I don't know. Or maybe it was under attack. All right. Students in my security class will be studying this kind of attack later. All right. I need more data. So my company happens to have another website with a different hosting company called HostMonster. I promise you, I'm not being funded by HostMonster. Okay, I should get HostMonster to I put an advertisement in my slides, be like, and pay me, of course, right? So basically, they did a test, and this person asked 3 different employees to collect page load times at different times of day over a 2-week period from Alentis and from HostMonster to see which one is faster. Okay? So, imagine, the claim is imaginary, excuse me, okay? Imagine that Alentis claims that the average load time of the 3 pages, including the worst times of day, so if I take any time of day, on average, it should be 6 seconds, which is, of course, ridiculous, all right? It shouldn't be 6 seconds. But let's say this is the claim. Nobody would wait for a 6-second website to load. Or maybe you do, I don't know, you know. So I'm going to go with this 2-tailed distribution for now, okay, in this demonstration, right? So, and my data looks something like this. It's Alentis' times and HostMonster's times, all right? And I'm going to do a traditional t-test on this thing. So where are you? Alentis, all right? So the load times, where is the Alentis data set? Is it here? Where are you? Pageloads.csv? All right, so again, it's a CSV file, 2 columns, Alentis and HostMonster. You can already see Alentis has some ridiculous loading times here and there. 500 seconds? Who was even patient enough to wait and time this damn thing, you know? 424 seconds, what's going on here? All right. 385 seconds. Now, we could say, just get rid of this times, right? You could say, oh, these are outliers, get rid of them. But the whole point of this test is to see what the average load time is, right? And there are customers who are waiting for 400 seconds, apparently. So it would be folly, maybe, to delete these outliers so quickly, all right? All right, so let's get these loading times and Alentis, all right? So the traditional approach looks like this. It's no surprise. I'm calculating the mean time of Alentis. It's about 20 seconds. That is slow. That's ridiculously slow, all right? And the standard deviation is 77 seconds. What on earth? That's a huge standard deviation, all right? And the cutoff we're interested in for a t-value, and we're going to use the qt function to tell us what is the cutoff for 0.025, and I'm doing a 2-tailed, I should be doing a 1-tailed, it doesn't matter, okay? And my degrees of freedom is this, all right? So the cutoff is about 1.98, all right? Oh, and I can do a t-test, fantastic. There's a t-test function I can use right inside R. Some of you discovered that for you. Yes, in the back. Question? The sound is not working? Hold on a second, my microphone. Oh, hello, is that working? Okay, the battery is actually dead. Okay, but can you hear me a little bit? Okay, then bear with me for a few more seconds. We're going to do this example and then we will switch up, okay? All right. Every rock star has a little crew, right? Like a little sound crew. Okay. All right. So let me just move ahead though in the meantime. So Alentis' mean time is this. The standard deviation is this. The cutoff t value is this. We can just, R has a t-test function. Did I not tell you this for your assignment? I'm sorry. Anyway, but it has a t-test function and you can use it. You can tell it your hypothesis mu, okay? And in this case, the alternative two-sided, you can just tell it that directly. And it computes things for you, tells you, here's your t-value, fantastic. Here's your p-value, excellent. Oh, excuse me. I'm going to mic up really quickly here. Is that better? Yes? Okay, thank you. So, all right. So the t-value, the p-value, it even gives you a nice confidence interval of the mean. Okay? So the confidence interval of the mean. Oh, look at that. The confidence interval of the mean actually includes 6 seconds. Though. How come? The mean was 20 and the hypothesis is 6. Well, this is the reason. The standard deviation is huge. All right. So my confidence interval includes 6. We cannot reject the claim. Boo. All right. So what should we do? Just tell Atlantis, you got me this time. All right. But let's just visualize this data for a second and see what's going on. Okay. How can this be? How can it possibly be that my data is telling me the mean is 20, the hypothesis is 6, and I cannot reject it? What's going on with this data set? Well, I'm going to visualize the data here, and I'm going to use, a density plot and also a box plot. I've just put them in the same space to save some space. Well, you can see that my data is largely just this one big peak, but there are blips all over the place, all the way down to 480 seconds. I have data that is like, I have real outliers. And when I look at the box plot, indeed, everything here is everything beyond, what is this? Like 20 seconds is an outlier. All right. So and remember, my mean is 20 seconds. It's like around here somewhere, right? My mean is around here. It's a very unlikely value. All right. Oh, rats, what should we do? Well, this is what we're going to do. First, we're going to cool down and take a break. Then we'll come back and see how we can get back to Atlantis without saying, hey, you guys are right. Here's my money. Keep taking your time. We don't want to do that, right? So let's take a little break. Let's just take about 10 minutes, okay? And I'll see you guys back here around 10:25 or so, all right? So.